Hey everyone, and welcome to this explainer. Whether you're a student currently navigating the kind of dense world of engineering chemistry, or you're just a curious mind taking a well-deserved break on YouTube, you are absolutely in the right place. Today, we're going to explore the hidden potential of some everyday materials. We're keeping things super calm, clear, and focused. No stressful lectures here, just a really fascinating look at the invisible forces that are quietly shaping our modern lives.
So let's just dive right into this with a simple question to kind of challenge what we all think we know. When you think of plastic, you almost definitely think of an insulator, right? It's the stuff that blocks electricity. It literally wraps around our charging cables to keep us from getting shocked. But what if the very material we use to block electricity could actually be engineered to conduct it?
The contrast we're looking at here is genuinely revolutionary. Most traditional polymeric materials are, well, they're pretty terrible conductors of electricity because they simply don't have enough free electrons to carry a current. So historically, we've used them almost exclusively as insulators. But engineering chemistry has introduced us to this incredibly special class called conducting polymers. And these materials, they have electrical conductivities perfectly on par with metallic conductors. No joke.
Let's quickly anchor ourselves with a clear definition straight from the source material. Conducting polymers are basically polymeric materials that can actually be used in place of metals because of their lightweight and low cost, all while still possessing that metallic-level conductivity. Just imagine getting the electrical performance of copper or steel, but with the flexibility, the cheapness, and the sheer lightness of everyday plastic. It's a total game changer.
All right, let's get into Section 1, Opening, the electron highway.
So notice the relationship here between the valence band, which is filled with electrons, and the conduction band, which is completely empty. For electricity to actually flow, electrons need to cross that empty space in the middle, what we call the Fermi energy gap. In most plastics, that gap is just way too wide. But in these special conducting polymers, the gap is surprisingly low, which means electrons become highly mobile throughout the entire material.
And this mobility happens because of something called the intensive conjugation of pi bonds. In simpler terms, these polymers have this alternating structure of single and double bonds right along their carbon chain. The orbitals of these conjugated pi electrons overlap across the entire backbone of the polymer. I actually like to think of this as an overlapping electron highway that just allows electricity to travel completely freely from one end of the plastic to the other.
Let's just take a quick breath and break that down into 3 super simple low-pressure steps. First, the polymer forms alternating double and single bonds. Second, those orbitals overlap to create a nice continuous path. And third, because of that awesome overlapping structure, the electrons only face a very low energy gap. That lets them easily jump from the valence band over to the conduction band. And bam, just like that, our plastic becomes a conductor. Now, the really crucial point here is that we can actually control and amplify this whole process through a technique called doping. Because these conducting polymers have low ionization potential and high electron affinities, they can easily be oxidized or reduced. So by adding a positive charge, which is oxidative doping, or a negative charge, reductive doping, we can drastically boost their ability to conduct. This is what takes them from a neat little lab trick to something truly useful in the real world. Which brings us to Section 2, Powering Our Everyday Tech. Think about all the modern, portable gadgets you use every single day. Because these materials are so incredibly easy to fabricate into any shape or design, they are increasingly being used in rechargeable batteries, the electronic displays on your phones, light-emitting diodes or LEDs, and even in photovoltaic solar devices and data storage. They're just seamlessly blending right into our daily tech routines.
To give you a more specific idea of what they can actually do, conducting polymers used in small, button-sized rechargeable batteries can produce a current density of up to 50 milliamps per square centimeter. For a material that is, at its core, a low-cost, lightweight plastic, generating that kind of current density is literally an unbelievable feat of engineering. And the reason this matters so much for our future is pretty simple. We are actively replacing heavy, rigid metals with materials that are low-cost, mechanically durable, and exceptionally light. This means our everyday devices can become way more efficient, much easier to carry around, and significantly cheaper to produce, all thanks to a really clever shift in how we structure polymers.
Let's shift gears a bit. Section 3, Sensing the World.
Because these polymers can detect really minute electrical changes, they're heavily utilized to create hypersensitive analytical sensors. Our source material highlights their use in monitoring a massive variety of conditions. We're talking everything from tracking human health via glucose and pH sensors, all the way to environmental monitoring of oxygen, nitrogen oxides, sulfur dioxide, and even ammonia.
It's actually quite fascinating when you stop to think about it. These modified plastics, they basically act as invisible sentinels in our world. They're just operating quietly in the background of factories, inside hospitals, and even in our own homes, constantly monitoring the air we breathe and the state of our personal health. They keep us safe and informed without ever demanding our attention.
Moving on to Section 4, Healing the Body.
So beyond just sensing things, these polymers can also act as ion exchangers. In very simple terms, membranes made from conducting polymers show what we call selective permeability. They essentially behave like tiny, smart microscopic gates that can be perfectly engineered to only let highly specific ions and gases pass through them.
By leveraging this totally brilliant smart gate property, medical engineers use conducting polymers for highly targeted medical treatments. The sources specifically point out their application in the controlled release of drugs inside the human body, as well as their highly specialized use in cancer chemotherapy. The polymer can slowly and deliberately release the exact amount of medicine needed, precisely where the body needs it the most.
This represents a massive, massive paradigm shift in how we view materials in medicine. For decades, plastics were just, well, they were just the simple inert containers that held your pills, right? Today, thanks to the chemistry of conduction and selective permeability, they are the active, life-saving devices that are actually administering the treatment. That is mind-blowing.
And finally, Section 5, a quiet future.
The main takeaway I want you to have from this whole revolution is one of subtle but massive transformation. We don't always hear about them in the news, but these low-cost, lightweight, and easily fabricated materials are silently revolutionizing the three most important pillars of human life: our tech, our health, and our energy systems. They really are an invisible force, steadily upgrading the very fabric of our modern world.
As the textbook elegantly summarizes, while most polymers are insulators, some polymers possess this unique electrical conductivity and can actively be used in place of metals due to their lightweight and low cost. It's a perfect reminder that in the wild world of advanced materials, a slight tweak in atomic structure, just giving electrons a highway to travel on, can completely rewrite the rules of what a material can actually do.
I'm going to leave you with that thought to ponder. As these hidden electron highways continue to branch out into new fields and cutting-edge technologies, what other invisible, highly engineered materials do you think are quietly shaping your world right this very second? Thank you so much for taking the time to learn and explore this explainer with me today. Stay curious, take it easy, and keep observing all the incredible science hiding in plain sight.